Okay, so we are picking up where we left off last time. Last time, we got through the idea of what is a sampling distribution. And so we talked about we need to know how different statistics work. And so the example that we did is we did sampling distributions of size 2. So we looked at all the samples of size 2. First, we did X bar, and we graphed all of them. Then we did the sample range, and we graphed all of them. And what we saw was that X bar was an unbiased estimator of mu. That's because X bar is centered at the true value of mu. But we saw in terms of sample range, if 7 is the population range, if we look at all these values, we're going to tend to underestimate. So what that tells us is if I have a sample and I take the range of that sample, it's probably an underestimate in the long run of the population range. The idea is we want to estimate various things about the population, and we need to know, is it going to be a good estimate or not? So let's move on to this next example that I said is kind of like what we did earlier. To determine how much homework time students will get in class, Mrs. Lynn has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the sample determines the number of minutes in class students get to work on homework. Mrs. Lynn claims that there are 200 chips in the bag and 100 of them are red. When Jenna selected a sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? Okay, so we're going to kind of break this down into into all of the different pieces and parts. Ultimately, what we care about is Mrs. Lynn lying to us? Right, so we expect half the chips in the bag to be red. When we take a sample of 20, how many do we expect to be red? 10. Right, so if we got 9 red, we're like, okay, that's not too bad. The question, though, is 7. Is that too far away? Right, is that going to be highly unlikely? So part A, what is the evidence that we have that less than half the chips in the bag are red? Well, we got 7 out of 20 are red. And that 7 out of 20 is less than half the chips. So that's the evidence that we have so far. We took one sample, and that one sample gave us a value that was less than 1/2. That does not necessarily mean that Mrs. Lynn is lying. There are 2 possibilities. So there are 2 explanations for that 7 out of 20. The first one, again, is that Lynn is lying. If we put that in context, what that means is less than half the chips in the bag are red. And that would make sense. Less than half the chips in the bag are red, so when we took out chips, less than half of them were red. What is the other possibility? Do you guys remember?
It's just sample variability.
Yeah, is it possible that we just happened to choose a sample where less than half were red? Yeah, and so the term like Matthew used that we talked about last class is sampling variability. So in words, what does that mean? We just happened to pull a sample where less than half are red. And so the question in statistics is, how do we figure out which one of these is more likely? There's no way that we're going to know for sure unless we go through the bag. So the only way to definitively be able to choose between these 2 is to go in through the bag. We're not actually going to do that, though. We're going to figure out which one is more likely. And so what we're going to do is, instead of thinking about this one sample of 20, we're going to look at a whole bunch of samples of size 20. And we talked about in the last class, we would have a computer do this. So we tell a computer we want a sample of size 20, and it's being chosen from a population of 200 where 100 of the chips are red and 100 of the chips are blue. Someone in like a computer science class would have programmed this and just said, pull 500 samples. And that, in the dot plot, is what those samples would have come up as. So first thing, let's make sure that we understand what this sample is showing us. So there's 1 dot in the graph at 0.8. What does this represent? So if we remember from reading this and what we did the other day, each dot, so we have to imagine that these are a bunch of dots, represents a sample. So that dot at point 8 represents one sample of size 20, where 0.8 of the chips are red. Well, that 0.8 would be 16 out of the 20. So that is a single sample out of all 500 where 0.8 of the chips are red. So we would say that's pretty unlikely. Possible, but pretty unlikely. So now we're getting to the final question, or really what we care about. Would it be surprising to get a sample proportion of 7 out of 20, which is 0.35, or smaller if the population proportion is really 0.5? Justify your answer. Okay, one thing I want to make sure is that we understand where this p equals 0.5 comes from. That's not random. That comes from how the problem was set up, where it says 200 chips, 100 of which are red. So in the initial simulation, we said half of the chips have to be red. That's why this p is 0.5. Second thing I want to make sure that we understand is it would be most logical if we get a sample proportion of 0.35 to look at just 0.35 on the figure. I think that's what makes the most sense logically, is if we got 0.35, why are we, just look at 0.35? That's a little misleading though. If we notice in the question, it says 0.35 or smaller. You're always going to look at the result that you got or more unusual, which in this case, is all of this, all of those samples. Okay, so again, if we imagine a bunch of dots there, is that unusual? It's kind of hard to tell because we don't actually have the dots, but what is considered unusual or surprising in stats? Colleen, I know you have it on the tip of your tongue. What is surprising? Less than 5%. Does it look like if we counted those dots up, they would be less than 5%? I'm going to say probably not. So would it be surprising? Not really. Because more than 5% of the samples have a sample proportion of 7 out of 20 or smaller. Okay, so I think when we've done this previously, we've had a pretty good idea up till D. And I think E is where we always get confused. Is there convincing evidence? So is there convincing evidence that less than half the chips in the bag are red? Explain your reasoning. So I'm going to try to frame this a little bit differently. The claim is that 50% are red. What actually happened is we got 35% are red. Okay, what do we trust more? The claim that someone tells us or the sample we actually took? Well, we actually took, right? We carried this out. I don't know Mrs. Lynn. I don't know if she's trustworthy. I'm going to trust the sample that I actually took. So then when I look up here, what's the likelihood of the sample that I actually took? If Mrs. Lynn is telling me the truth, if this claim is true, well, it's fairly likely. It's fairly likely. So do I really have evidence to dispute this 50%? No. Probably sampling variability. So is there convincing evidence less than half are red? No. No, and we would say, if we're going to put this in words, a sample where 7 out of 20 of the chips are red, or it's 7 out of 20 or less. So that sample is fairly likely to happen by chance, even if half the chips are red. Okay, one thing that I want to be very clear about with this is we did not prove that the claim is true. So we did not prove that half the chips in the bag are red. Could be that half are red, or less than half are red, or more than half are red. We proved nothing. So we've proved nothing at all. We've just said we don't have sufficient evidence that less than half are red. That's all we can say. We cannot say, yeah, definitively half of them are red. We can't say less than half are red, even if we had convincing evidence. So even if we had gotten this proportion of 0.15, that still does not mean that less than half are red. The only way to definitively know with 100% certainty is to actually go through the bag. Okay, questions for me? Okay. Let's look at some more. Okay, so we've got one more page of notes. We're going to finish these notes and then we will move on with our lives. So I've told you that one thing people get really confused on is this term distribution. Okay, so I know we've written the definition approximately 12 times. We're going to write the definition one more time. A distribution tells all the possible values and how likely they occur. So there are 3 different distributions. We can have the distribution of the population. Well, this is exactly what it sounds like. It tells us the possible values in the population and how often they occur. On the other hand, we could have the distribution of the sample. That's the possible values in the sample and how often they occur. And then we could have the sample statistic. And the term we've been using for that is sampling distribution. Okay. So what I want to do is I want to think back to the example that we did of the father with 4 kids. And we said that those kids were aged 12, 15, 16, and 19. And we are going to talk about all of these different distributions. So first of all, before we get into the other ones, remember we've talked about this could be a table or it could be in a graph. So those are the 2 most common ways to display a distribution. If we did the population, The population distribution is going to show everyone in the population, which in this case is just the 4 kids. So we're going to get 12, 13, 14, 15, 16, 17, 18, 19, 20. So we would have our kid at 12, there's the kid at 15, the kid who's 16, and the kid at 19. That is the population. It's a very small population, but that's the population. Every dot represents one individual, which in this case is one of the children, and how old they are. Now, if you remember, we looked at samples of size 2. And so we said we could get 12 and 15, 12 and 16, 12 and 19, so on and so forth. So we said there were 6 samples. If we're looking at the distribution of the sample, it's 1 sample. So we might decide to take a look at this sample, the sample of 12 and 15. So then we have a dot at 12 and a dot at 15. Again, each dot represents an individual, and it is an individual in that sample. All right, so if I took a different sample of size 2, there would be different people there. Now, these distributions are not that exciting, right? If I look at the population, it tells me there's only 4 possibilities, and they happen once. The sampling distributions then are what we had on the previous page. Sampling distribution, every dot represents a sample. And it's the same statistic for each sample. So I'm not going to redraw them because you have them on the previous page. But the big difference is every dot is an entire sample. Okay, I want to give us a big key as to how people lose credit on quizzes, tests, the AP test, so on and so forth. You must avoid ambiguity. Okay, so for example, a lot of people will say something like, when sample size increases, variability decreases. I would be honest and say that's actually more specific than some of us write, but that's not specific enough. The questions that arise for me when I read that is the variability of what? Which distribution are you talking about? All right, so what's my context? Am I talking about the population? Am I talking about the sample? Am I talking about the sampling distribution? So we need to specify these. Okay, we got a few more things, and then we are done with notes for today. We've used the terms biased and unbiased quite a bit, but we haven't written down any definitions. So I want to put into words what is a biased estimator and an unbiased estimator. Unbiased estimator means these estimates or these statistics are not consistently too high or too low, for estimating the population parameter. When taking many random samples. So if we take a whole bunch of samples, we're not going to consistently over or underestimate. Like we saw with the father one that we did on the previous page, when we were taking sample means, the X bar, sometimes it was too low, sometimes it was too high. But over the long run, it centered out at the right value. On the other hand, biased estimates are consistently higher or lower than the parameter. So like we saw with sample range, most of the estimates were below the population range. Two things very important for us to know. First one is unbiased does not mean that the statistic is perfect. Bless you. It doesn't even mean really that it's a single good estimate. It means it's a good estimate in the long run if we were to take many samples. It doesn't mean a single sample is good, and it doesn't mean that it's perfect. The other one that's big is there are no guarantees if the sampling process is biased. And by biased, I mean flawed. So if we have a poor sample, that really, like if our sampling process is poor, then there's no guarantees in terms of whether our estimator will be biased or not. You need to just know some of the biased and unbiased ones. So I'm going to tell you the ones that are most common. Unbiased. You're fine. Okay, one that you probably know. X bar. So that's the sample mean. Sample mean is an unbiased estimator of, what do you think? Population mean. Great. Sample median is unbiased. There's no symbol for that. And that is an unbiased estimator of population median. The other one is sample variance. Sample variance. So that's one that we tend to forget what that word means. It's just the square of standard deviation. And then one more that is unbiased is p hat. And in words, if we remember, p hat is sample proportion. So those four are all unbiased. There's more, but those are the big ones. If we're looking at biased, the one that comes up a lot, variance is unbiased. Standard deviation, though, is biased. So what that means is if I took a whole bunch of sample standard deviations, they're going to tend to overestimate or underestimate the population standard deviation. Some ones that you can probably guess, maximum is biased, minimum is biased, and there's more. The ones that are most important for you to know is to know that X bar and P hat are unbiased. Those are the most important. And then I think it tends to be tough to remember that variance is unbiased, but standard deviation is biased. The yellow ones, though, are most important. And that'll make sense because moving on with notes, we're only going to look at mean and proportion. Okay. Do I have your attention for 5 more minutes to finish this? Okay. How do we reduce the variability of a statistic? So for example, if we were to look at the sampling distribution of S. So what I mean by that is we're taking all the samples of size 2 or 3 or 4, let's say 4, all the samples of size 4, we're finding S for every sample and we're graphing them. How do we get less variability? So similar to with the tank problem, we had those 3 dot plots up, and we said we needed a statistic that was centered at 100 and had less variability. Did we talk about how to reduce the variability? Did I tell you the one way? I think I did. Very last thing we did? Don't remember? Okay, biggest one. Larger sample. I don't mean take more samples. So with the German tank problem, we were taking samples of size 7. If we had taken samples of size 10 for every single statistic, the spread would have gotten smaller. Biased or not. So bigger samples. The second one, this is going to be a throwback, a stratified design. So if we stratify in some way, that will often lead to less variability. Okay, something that is kind of counterintuitive. If we take a bigger sample, the variability of the statistic will go down. What about, though, the population? We might think the same thing. Oh, if the population's bigger, there's going to be less variability in the statistic. That's not the case. So what effect does the population have on the variability of the statistic? None. Okay, last thing to talk about is the terms accuracy and precision. So you've heard those before. My guess is maybe in chemistry. Those are not the terms we use in statistics, though. Have you guys ever seen in a science class the example of like a dartboard and throwing darts at the dartboard? And normally there's an example given of accuracy and an example given of precision. What is accuracy if you're throwing darts at a dartboard? Have we ever seen that? No? Okay. You guys know what I mean by a dartboard, right? If I'm talking about accuracy, I'm getting a bullseye, or I'm getting pretty close to the center. If I'm talking about precision, has nothing to do with the bullseye. Instead, it means every time I'm throwing, they're getting pretty close together. So if we think of, this is what I'm trying to say, this right here, that's accurate. This right here is precise. So I hit the bullseye, I'm accurate. I throw a bunch of them, I don't necessarily hit the bullseye, but they're all pretty similar. That has to do with precision. So in terms of bias and variability, accurate means that our statistic is unbiased, which has to do with the center of the sampling distribution. So like I said with the German tank problem, we're looking at, was the center at 100? In the long run, looking at many samples, am I around 100? I'm not over or underestimating in the long run. Precision, on the other hand, has to do with variability. So if something is precise, if a statistic is precise, it has low variability, meaning it relates to spread. Questions for me?